Hi everyone, welcome back. So in the last video, we talked about how pressure and volume are related using Boyle's law. And in this video, we're going to talk about how temperature and volume of a gas are related using Charles' law. So Charles' law states that if we increase the temperature of a gas sample, the motion or kinetic energy of the gas particles is also going to increase. So if we heat up our sample of gas, those gas particles are going to start moving really fast. We're giving them kinetic energy, energy of motion, and they're going to start colliding with each other and with the sides of the container. So if the amount and the pressure of the gas is held constant, Charles' law says that the volume of the container will increase as we increase that temperature. Okay, so the relationship between temperature and volume is direct. It's not inverse like Boyle's law, it's actually direct. So as we increase the temperature, the volume of the container will also increase. So let's take a look at that a little closer. So in Charles' law, the Kelvin temperature of a gas is directly related to its volume. Notice that they really emphasize the temperatures in Kelvin, and remember that's because these gas laws were derived using the Kelvin temperature scale. So you need to make sure anytime you see a temperature for these gas laws, the way I do it is I just immediately convert it to Kelvin. So if I see degrees Celsius in these gas law problems, I just right away I convert to Kelvin, and you'll be given that conversion equation on an exam. So just like in Boyle's law, there are things that we need to hold constant so that we can actually compare the relationship between a couple different values. So in Charles' law, we actually hold pressure and moles of gas constant so that we can see how the volume and the temperature are related. And they're related according to that equation there. So remember, moles of a gas, we use the symbol N, lowercase n for, and pressure is just a capital P. Okay, just a review for you there. So in Charles' law, when the temperature of a sample of a gas increases, its volume also increases at constant pressure. So looking over here at our initial gas sample, we've got our gas in a container there with a movable piston, and we've got our temperature. Our initial temperature T1 is 200 Kelvin, and our initial volume V1 is 1 liter. So we raise the temperature, right? We've got just a little bit of heat hitting the container here, but over here we've raised the temperature quite a bit, right? Bigger flame. So now you can see, because we can move that piston up, right? As we're heating up our gas, we're making those molecules, we're giving them lots of energy. They're going to start rapidly colliding with each other and with the container, and that's going to push that piston up because of the increase in volume. See, we go from 1 liter to 2 liters. Okay, so as we increase the temperature to 400 Kelvin, we also increase the volume to 2 liters in this example. Okay, direct relationship, not inverse. As temperature increases, volume also increases, as long as we're holding pressure and moles constant. All right, so let's go ahead and do a learning check. So again, you don't need to memorize these equations, so let me just write it here for you. We got V1 over T1 equals V2 over T2. You will actually start to memorize these a little bit as you keep working with them. But yeah. So a sample of oxygen gas has a volume of 420 mils at a temperature of 18 degrees Celsius. Oh, degrees Celsius. What do we need to do right away? Yeah, let's convert that to Kelvin. Okay, so let's go ahead and convert. Step 1, convert to Kelvin. All right, so what is the equation for converting to Kelvin? If you remember, that's great. If you don't, I'm going to write it down for you, so don't worry. So Kelvin, and this will be on your exam as well. I'll give you this equation. So Kelvin equals degrees Celsius plus 273. All right, so it looks like my temperature is 18, and then plus 273. So that's going to give me 291 Kelvin. Okay, so that's my temperature in Kelvin. All right, now we're not done yet though, so let's keep working. So step 2, we are actually going to do the solving with Charles' law. So we have our volume, we have a temperature, and then it says at what temperature in degrees Celsius, so we will have to convert back to Celsius, but you need to convert to Kelvin to use this equation, and then you can convert back. I know, kind of a pain in the butt, but we got to do it. So at what temperature in degrees Celsius will the volume of oxygen be 640 mils if pressure and moles are constant? Okay, so let's break this down. So we got, where is our V1? So we start with a volume of 420 mils. So let's call that V1. And a temperature, I'm actually going to label it over here. This is our T1 because I converted it, right? So maybe I'll draw a little arrow. And then at what temperature? So that's going to be our T2, right? That's the thing we're going to be solving for. So let me go ahead and highlight that. And at what temperature will the volume of oxygen be 640 mils? So this is going to be our V2, right? Final volume. All right, so let's plug these values in. So we got V1 over T1 equals V2 over T2. I'm going to solve for my unknown variable first. So remember, you can cross multiply in this situation because you've got two things being divided on one side, and on the other side you've also got two things being divided. So we can cross multiply. So let's get, when we do that, we get V1 T2 equals V2 T1. Okay, and then we can divide both sides by V1. Sorry, it's kind of hard to see there. Divide both sides by V1 to get T2 alone. And let's continue this over here. So now we got T2 equals V2 T1 over V1. Whew, all right, so let's plug in those values. So we got V2 is, we said, 640 mils. T1 is, we said, 291 Kelvin. And then V1 is 420. Oops. Oh, yeah, that's right. 420 mils. All right, so notice, let's do a quick unit check. We can cancel out those mils, and we're left with Kelvin, which is a unit of temperature, which is what we want to be in eventually. So perfect. So actually, I want to color code this just so we don't get lost in the sauce here. So, okay, so now we got T2, 43 Kelvin. Are we done? No, we want to end up in degrees Celsius, right? We were asked for our we were asked for our temperature in degrees Celsius. So we got to convert. So they're trying to trick you here. Don't let them fool you. So we'll convert, and the way that we convert from Kelvin to Celsius is just like we did before, except now we've got our Kelvin and we want to find our Celsius. So we're going to use that equation in yellow there. So let's make a step 3 here. And we'll say convert back to degrees Celsius. Whoops. Okay, so we have 443 Kelvin equals degrees Celsius plus 273 Kelvin is 170 degrees Celsius. So this would be our final answer. So let's go back here, get rid of that. Let's see if that's on the list. Yes, it is. So there's our final answer, B. Okay, so remember, the key with these questions or with these problems is to make sure that you're checking your units the entire time. If you're given a temperature in something other than Kelvin, convert to Kelvin first, and then if you have to convert back, you can in the last step. And then also, my other big tip is just to look at the units. in your equation to figure out what type of gas law you are going to use, okay? So what gas law am I going to use? A lot of times after you label all of the different types of units you have or variables you have, you can kind of see more clearly which gas law you can use, okay? All right, so that's it for Charles' law. I'll see you in the next video for Gay-Lussac's law.